August 14, 1942. Skies over Iceland. A German Focke-Wulf Fw-200 Condor patrol bomber cruised through the Arctic air, its crew scanning the waters below for Allied convoys. The four-man crew had flown dozens of similar missions, confident in their aircraft's range and their own experience navigating the treacherous North Atlantic routes. What they didn't know was that diving down from 25,000 feet above them was an American fighter unlike anything they had ever encountered, a twin-boomed, twin-engined Lightning that would rewrite the rules of air combat and earn a nickname that would strike fear into Luftwaffe pilots across Europe and North Africa, der Gabelschwanz Teufel, the fork-tailed devil. The Condor's crew had every reason to feel secure. Their aircraft was one of the most advanced long-range patrol bombers in the world, capable of staying aloft for over 14 hours while covering vast expanses of ocean. German intelligence had assured them that American fighters lacked the range to operate effectively in these waters, and their own Luftwaffe escorts controlled most of the skies over occupied Europe. The idea that an enemy fighter could appear without warning in this remote corner of the Atlantic seemed impossible. That impossibility was about to become reality as the distinctive silhouette of the P-38 Lightning closed in at over 400 miles per hour, its twin engines driving it through the thin air with a speed and power that defied every assumption about what a fighter aircraft could achieve. The challenge that started it all. The story of the Lightning began 5 years earlier in the bureaucratic corridors of Wright Field, Ohio, where U.S. Army Air Corps planners were grappling with an uncomfortable truth. American fighter aircraft were falling dangerously behind European developments. In 1937, the Air Corps issued Circular Proposal X608, one of the most demanding fighter specifications in aviation history. They wanted an interceptor capable of flying 360 miles per hour at 20,000 feet, faster than any existing fighter, while climbing to that altitude in under 6 minutes and maintaining lethal effectiveness at ranges that would make long-range bomber escort missions possible for the first time. The requirements seemed almost fantastical. Existing American fighters like the Curtiss P-36 Hawk could barely reach 300 miles per hour in level flight, and their service ceilings and climb rates were far below what the specification demanded. European fighters were advancing rapidly, with new German and British designs promising performance levels that would make American aircraft obsolete before they even entered service. The Army needed a quantum leap in capability, not just an incremental improvement. Most established aircraft manufacturers examined the requirements and politely declined to submit proposals. Boeing, with extensive experience in large aircraft, considered the specifications technically impossible within reasonable cost constraints. Curtiss-Wright, America's premier fighter manufacturer, submitted a conventional single-engine design that failed to meet the speed requirements by a significant margin. The consensus among aviation experts was that the Army was asking for the impossible. But at Lockheed Corporation, a small company headquartered in Burbank, California, Chief Engineer Hall L. Hibbard and his brilliant young assistant, Clarence Kelly Johnson, saw opportunity where others saw impossibility. Lockheed was an ambitious company with limited military experience, having built primarily civilian airliners and transport aircraft. They desperately needed a major military contract to establish themselves as a serious competitor to established manufacturers like Boeing, Douglas, and Curtiss-Wright. Johnson, only 27 years old but already recognized as one of aviation's most innovative thinkers, approached the problem with mathematical precision. He calculated that the power-to-weight ratios required by the specification could only be achieved with twin engines, but conventional twin-engine configurations were too heavy and draggy to meet the speed requirements. The solution required completely reimagining what a fighter aircraft could be, challenging fundamental assumptions about aircraft design that had dominated aviation since the Wright brothers' first flight. Working with a small team of engineers in a converted garage, Johnson developed a radical concept: two powerful Allison V-1710 liquid-cooled engines mounted in streamlined booms, connected by a central nacelle housing the pilot and armament. The configuration looked like no fighter anyone had ever seen, more like a science fiction illustration than a practical military aircraft. But the mathematics were compelling. The design promised not just to meet the Army's requirements, but to exceed them dramatically. The opposition's confidence. Across the Atlantic, German aircraft designers were pursuing their own philosophy of fighter development, one based on entirely different principles from the American approach. The Messerschmitt Bf 109, which had become the backbone of the rapidly expanding Luftwaffe, represented what German engineers considered the pinnacle of fighter design: compact, lightweight, and devastatingly effective in the hands of properly trained pilots. Willy Messerschmitt's design philosophy emphasized simplicity and pilot skill over technological complexity. The Bf 109 was built around a single powerful Daimler-Benz engine, with every component optimized for minimum weight and maximum performance. German pilots were trained extensively in aerial gunnery and combat maneuvering, developing skills that could extract maximum effectiveness from relatively simple aircraft. The combination of superior training and efficient design had proven devastatingly effective against every opponent the Luftwaffe had faced.
British. The ammunition itself was a marvel of engineering. Each 37mm shell was a precision-manufactured projectile containing either high explosive, armor-piercing, or incendiary compounds. The high-explosive shells, designated M54, contained 49 grams of Composition A explosive, enough to create a blast radius of several meters. The armor-piercing shells, known as M80, could penetrate up to 30 millimeters of hardened steel at 500 meters range. Most remarkably, the shells were fitted with M48 point-detonating fuses that could be set for different sensitivity levels, allowing pilots to engage different types of targets effectively. The ballistic performance was equally impressive. The M4 cannon could fire at rates up to 150 rounds per minute, though most pilots used it in semi-automatic mode for accuracy. The muzzle velocity of 2,000 feet per second gave the shells a flat trajectory out to 2,000 yards, far beyond the effective range of machine guns. Perhaps most importantly, the shells retained their destructive power at long range, unlike machine gun bullets that lost energy and effectiveness with distance. Engineering challenges and innovations. Installing such a powerful weapon in a fighter aircraft presented unprecedented engineering challenges. The recoil force generated by the M4 cannon was enormous, approximately 1,200 pounds of force with each shot. This was enough to slow the aircraft noticeably and throw off a pilot's aim if not properly managed. Bell's engineers, led by structural specialist Dr. Margaret Thompson Chen, one of the few women in aircraft design at the time, developed an innovative recoil absorption system. The cannon was mounted in a specially designed cradle that incorporated hydraulic dampeners and spring assemblies to absorb the recoil energy. The mounting system distributed the force throughout the aircraft's structure rather than concentrating it at a single point. This required strengthening the entire forward fuselage with additional steel reinforcement rings and longerons, adding weight but ensuring the aircraft could withstand thousands of firing cycles. The ammunition storage and feeding system presented another challenge. The 37mm shells were far too large for conventional ammunition boxes. Bell's design team, working with ordnance specialist Colonel James F. Eastham from Wright Field, developed a unique rotary magazine system that held 30 rounds in a cylindrical container located behind the pilot's seat. The feeding mechanism used a pneumatic system to move the heavy shells from the magazine to the cannon's chamber, ensuring reliable operation even under high-G maneuvering. The weapon's fire control system was equally sophisticated. Unlike machine guns that could be aimed by spray and pray tactics, the 37mm cannon required precision shooting. Bell collaborated with the Sperry Corporation to develop an advanced computing gun sight that could calculate the proper lead angle for engaging maneuvering targets. The N3A gun sight incorporated gyroscopic stabilization and automatic range calculation, making it one of the most advanced fire control systems of its time. Cooling the massive cannon presented yet another engineering hurdle. The M4 generated tremendous heat during firing, enough to warp the barrel if not properly managed. The solution involved a complex cooling system that circulated engine coolant through jackets surrounding the cannon barrel. This system added weight and complexity, but was essential for sustained firing operations. Early development and testing phases. The first prototype P-39, designated XP-39, took to the skies on April 6, 1938 from Bell's test facility at Niagara Falls, New York. Chief Test Pilot James Taylor reported that the aircraft flew well, but noted significant vibration when the cannon was fired. The initial test program, conducted over the summer of 1938, revealed both the weapon's potential and its problems. During early firing tests conducted over Lake Erie, the cannon demonstrated devastating effectiveness against target drones and towed targets. A single high-explosive shell could completely destroy a fabric-covered target aircraft, while armor-piercing rounds punched clean through steel plates that would stop dozens of machine gun bullets. The accuracy was remarkable. Skilled pilots could hit man-sized targets at ranges exceeding 1,000 yards. Perhaps most importantly, the shells retained their destructive power at long range, unlike machine gun bullets that lost energy and effectiveness with distance. The ammunition proved to be both a blessing and a curse. The high-explosive shells were devastatingly effective against bombers and ground targets, capable of destroying targets that would require sustained machine gun fire to disable. However, the shells were expensive and complex to manufacture, costing approximately $12 each compared to just pennies for machine gun bullets. The weight of the ammunition also limited the aircraft's range and performance. 30 rounds of 37mm ammunition weighed over 80 pounds, equivalent to more than 2,000 rounds of .50 caliber ammunition. American and British skepticism.
British. The aircraft could climb at an initial rate of 3,300 feet per minute, faster than most existing fighters' maximum climb rates, and reach speeds approaching 400 miles per hour in level flight, making it 100 miles per hour faster than any operational fighter in the world. More impressively, it maintained this performance advantage across a wide range of altitudes and flight conditions, suggesting that the basic design concept was fundamentally sound rather than optimized for specific test conditions. During a transcontinental speed demonstration on February 11, 1939, Kelsey flew from Mitchell Field, New York, to Marchfield, California, in 7 hours and 48 minutes, setting a new coast-to-coast record that captured national headlines and international attention. The flight covered 2,400 miles at an average speed of over 300 miles per hour, including fuel stops and navigation delays, demonstrating practical long-range capabilities that existing military aircraft could not approach. The demonstration flight revealed capabilities that existing fighter doctrine couldn't adequately address. Here was an aircraft that could outrun, outclimb, and outrange every operational fighter while carrying more firepower than most light bombers. Traditional tactics based on numerical superiority and close-in dogfighting seemed inadequate against an opponent that could choose when and where to fight while maintaining the option to disengage at will. Foreign intelligence services took careful note of the Lightning's performance. British technical observers, who maintained close relationships with American aircraft manufacturers, obtained detailed performance data that influenced their own fighter development programs. German intelligence officers, working through a network of technical contacts and industrial espionage, compiled comprehensive assessments of the Lightning's capabilities and potential tactical applications. The turbocharger system represented perhaps the most significant technological advancement incorporated into the Lightning.
These devices, essentially exhaust-driven superchargers, captured energy from the engine's exhaust gases to drive centrifugal compressors that maintained intake manifold pressure at high altitudes. The result was an engine that could maintain sea-level power output up to altitudes of 25,000 feet or higher, giving the P-38 performance advantages that increased dramatically with altitude. This high-altitude capability would prove strategically significant as the war progressed. Bomber formations operating at maximum altitude to avoid anti-aircraft fire and interceptors found that P-38 escorts could maintain formation effectively, while most other fighters struggled to match their performance. The Lightning's ability to fight effectively above 30,000 feet gave Allied bomber formations a protective capability that enemy fighters often couldn't match. Early skepticism and problems. Despite its impressive specifications and record-breaking performance demonstrations, the Lightning faced significant skepticism from both American military leaders and potential foreign customers. The aircraft was expensive, approximately twice the cost of conventional single-engine fighters, and mechanically complex in ways that raised concerns about reliability and maintenance requirements in combat conditions. Early test flights revealed serious aerodynamic problems that threatened the entire P-38 program. During high-speed dives, the aircraft developed a dangerous tendency for the controls to lock up in a condition that test pilots termed compressibility. At speeds approaching Mach 0.68, shock waves forming over the wing's upper surface would cause the tail to buffet violently and the nose to drop uncontrollably, forcing the aircraft into an increasingly steep dive from which recovery became impossible. The compressibility problem killed several test pilots and threatened to derail the entire P-38 program. Test pilot Ralph Verdon, an experienced aviator with extensive knowledge of high-speed flight characteristics, was killed in November 1941 when his aircraft entered an unrecoverable dive during evaluation of proposed solutions to the control lockup problem. The crash occurred despite specific warnings about speed limitations and detailed instructions about avoiding high-speed maneuvers at low altitudes. Lockheed engineers struggled for months to understand and solve the compressibility problem, which seemed to defy conventional aerodynamic theory. The phenomenon was related to early manifestations of transonic flight effects that wouldn't be fully understood until after the war, when systematic research into supersonic flight began in earnest. Eventually, engineers developed dive recovery flaps that could be deployed to disrupt the airflow patterns causing control lockup, but the solution wasn't implemented until 1943. The British Royal Air Force, initially enthusiastic about the Lightning's performance potential, cancelled their substantial orders after extensive evaluation of early production aircraft. RAF test pilots found the cockpit inadequately heated for European winter conditions and criticized the aircraft's roll rate and high-speed handling characteristics. Their assessment, documented in detailed technical reports, seemed to confirm German intelligence conclusions that the Lightning was an interesting experiment but not a practical combat aircraft. British test pilot reports noted that while the P-38 was exceptionally fast in straight-line flight and possessed outstanding climb performance, it lacked the instantaneous maneuverability that characterized successful European fighters. The aircraft required significant pilot input to change direction quickly, and its large size made it easy for enemy pilots to spot and track during combat. These limitations suggested that the Lightning might be vulnerable in the turning fights that characterized most aerial combat encounters.
British production delays compounded the program's problems. Lockheed's limited manufacturing capacity and the complexity of the aircraft's systems meant that deliveries proceeded slowly, despite urgent military requirements. By December 7, 1941, when the United States entered the war, the Army Air Forces had only 69 operational P-38s scattered across various training and testing facilities. The Lightning represented future potential rather than immediate capability when America needed every available fighter aircraft. The pilots who would make the difference. While engineers worked to refine the Lightning's design and solve its technical problems, a new generation of American pilots began learning to harness its unique capabilities. These young men, many barely out of their teens, faced the challenge of mastering not just basic flying skills, but complex systems management far more demanding than any single-engine fighter required. Operating a P-38 effectively meant managing two engines, understanding turbocharger operation, monitoring multiple fuel systems, and maximizing the aircraft's range and altitude advantages through careful flight planning and execution. The training program developed for P-38 pilots was necessarily more comprehensive than programs for conventional fighters. Pilots needed to understand engine management techniques that would maximize performance while avoiding mechanical failures that could prove fatal during combat. They learned to coordinate throttle, propeller pitch, and turbocharger controls for both engines simultaneously while maintaining formation flight and preparing for combat maneuvering. Navigation training was particularly critical for P-38 pilots, since the aircraft's long range meant they would often operate far from friendly territory for extended periods. Dead reckoning navigation, celestial navigation, and radio navigation techniques all became essential skills for pilots who might need to find their way home across hundreds of miles of ocean or enemy territory. The responsibility of managing complex navigation requirements while remaining alert for enemy aircraft created workload challenges that many pilots found initially overwhelming. Richard Bong, a young farm boy from Poplar, Wisconsin, exemplified the new generation of pilots learning to fly the Lightning. Bong's rural background had given him mechanical aptitude and spatial awareness that translated well to managing complex aircraft systems, but he still required extensive training to master the P-38's unique flight characteristics. His early training reports noted difficulties with engine management and formation flying that were typical of pilots transitioning to the Lightning from simpler aircraft. Thomas McGuire, a determined young man from Ridgewood, New Jersey, brought a different background to P-38 training but faced similar challenges in mastering the aircraft's systems and tactics. McGuire's competitive nature and methodical approach to learning served him well in understanding the technical aspects of Lightning operation, but he initially struggled with the coordination required to manage two engines effectively during combat maneuvering. Both Bong and McGuire would eventually become America's highest-scoring aces flying P-38s. But in 1942, they were still learning fundamental techniques for exploiting the Lightning's advantages while compensating for its limitations. Their training experience reflected the broader challenges facing all P-38 pilots, learning to think differently about air combat in an aircraft that didn't fit any existing tactical doctrine. The doctrinal revolution. The P-38's unique capabilities forced American military planners to reconsider fundamental assumptions about fighter operations and tactical employment. Traditional fighter doctrine emphasized close-range combat and air superiority missions flown relatively close to friendly bases. The Lightning's range and firepower suggested new possibilities: long-range escort missions, deep penetration strikes against ground targets, and reconnaissance missions that could provide strategic intelligence from areas no other aircraft could reach. Fighter tactics developed during World War I and refined during the interwar period assumed that aerial combat would consist primarily of turning fights between roughly equivalent aircraft. Success depended on pilot skill, numerical superiority, and tactical surprise rather than technological advantages. The Lightning's performance characteristics suggested that these assumptions might no longer be valid when one side possessed significant technological superiority. American tactical theorists began developing new concepts for exploiting the P-38's advantages while minimizing its vulnerabilities. Hit-and-run tactics that emphasized the Lightning's speed and climb rate could allow P-38 pilots to engage when conditions were favorable and disengage when they weren't. The aircraft's high-altitude performance suggested that Lightning formations could patrol above enemy fighters, diving down to attack when opportunities presented themselves while retaining the option to climb back to safety. The concentrated firepower of the P-38's armament suggested new approaches to bomber escort missions. Rather than mixing it up in turning fights with enemy interceptors,
Lightning pilots could focus on destroying enemy aircraft quickly with concentrated bursts of fire, then moving on to engage other threats. This approach required more precise gunnery than traditional fighter tactics, but promised greater effectiveness when properly executed. Long-range operations became possible for the first time with the Lightning's Fw capacity and twin-engine reliability. Fighter sweeps hundreds of miles behind enemy lines could disrupt enemy operations and provide intelligence about enemy dispositions and activities. Escort missions could accompany bomber formations to targets that had previously been beyond fighter range, dramatically expanding the scope of possible bombing operations. The industrial challenge. Manufacturing the P-38 in quantity presented challenges that reflected broader issues in American military aircraft production. Lockheed's limited production capacity meant that even with expanded facilities and workforce, Lightning production proceeded slowly compared to simpler aircraft. Each P-38 required approximately twice as many manufacturing hours as a single-engine fighter, and the complexity of its systems demanded more skilled workers and more extensive quality control procedures. The aircraft's twin engines required coordinated production of power plants that were also needed for other military aircraft. Allison V-1710 engines powered not only P-38s, but also P-40 Warhawks and P-51 Mustangs in early versions, creating competition for limited engine production capacity. Turbocharger production presented additional bottlenecks, since these complex devices were manufactured by specialized companies with limited capacity for rapid expansion. Lockheed was forced to subcontract major components to other manufacturers, creating quality control challenges and coordination problems that affected production schedules. The aircraft's limited experience with large-scale military production meant they had to develop new manufacturing techniques and management systems while simultaneously trying to increase production rates and improve product quality. Despite these challenges, Lockheed's engineers and production specialists gradually solved the manufacturing problems that initially limited Lightning production. New assembly techniques reduced manufacturing time while maintaining quality standards, and improved supplier relationships ensured more reliable delivery of components and materials. By late 1942, production rates were approaching levels that could support significant combat operations, setting the stage for revolution. By mid-1942, the stage was set for one of aviation history's most significant technological confrontations. German pilots, supremely confident in their aircraft and tactics, controlled the skies over much of Europe and North Africa. Their single-engine fighters had proven superior to every opponent they had faced, from desperate British defenders during the Battle of Britain to Soviet Air Force units during the early stages of Operation Barbarossa. The Luftwaffe training programs had produced a generation of highly skilled pilots who understood how to extract maximum performance from their aircraft while exploiting the weaknesses of enemy fighters. German tactical doctrine, refined through years of combat experience, emphasized aggressive attacks and superior positioning that could overcome numerical disadvantages. The psychological advantages of consistent victory had created an aura of invincibility that demoralized enemy pilots before combat even began. American forces were finally beginning to receive P-38s in numbers that could support significant combat operations, but the aircraft remained largely untested against first-line opposition. Training squadrons were still developing tactics appropriate for an aircraft that didn't fit any existing operational doctrine, while maintenance personnel learned to service complex systems that required new tools and techniques. The Lightning's unique configuration required new approaches to formation flying, gunnery, and combat maneuvering that would take months to perfect through practical experience. Pilots trained on conventional fighters had to unlearn habits and techniques that were inappropriate for the P-38's unique flight characteristics. The process of developing effective tactics would necessarily occur during combat operations, with all the risks that implied. Intelligence assessments on both sides reflected incomplete understanding of what would happen when these different philosophies of air combat collided. German analysts, confident in their proven tactics and experienced pilots, saw little threat from American aircraft that violated established principles of fighter design. American planners, aware of the Lightning's impressive specifications but uncertain about its combat effectiveness, hoped that technological superiority could compensate for limited pilot experience and untested tactics.
The first encounters between German pilots and P-38 Lightnings would reveal whether Johnson's revolutionary design could live up to its theoretical promise when faced with the reality of aerial combat. In the skies over Iceland, North Africa, and the Mediterranean, American pilots would discover whether their unusual twin-engine fighter could challenge the supremacy of the Luftwaffe's battle-tested single-engine interceptors.
British-German pilot Hans-Joachim Massey, one of the Luftwaffe's most successful aces with 158 confirmed victories, encountered P-38s during operations over Egypt and reported his frustration with an opponent that refused to fight according to established rules. Massey's combat reports described American pilots who would engage only when conditions favored them, using superior speed and climb rate to dictate the terms of combat while avoiding situations where German experience provided advantages. The birth of der Gabelschwanz Teufel. The nickname that would become synonymous with the P-38 Lightning emerged from the chaos of North African combat operations. German ground troops, under constant attack from Lightning fighter bombers, began referring to the distinctive twin-boomed aircraft as der Gabelschwanz Teufel, the fork-tailed devil. The name reflected both the aircraft's unmistakable silhouette and the psychological impact of its concentrated firepower on troops who had no effective defense against high-speed, low-altitude attacks. By April 1943, the 82nd Fighter Group had refined its tactics to the point where German pilots no longer dismissed P-38 formations as easy targets. On April 5th, 26 P-38s claimed 31 enemy aircraft destroyed in a single engagement, establishing local air superiority in a way that traditional fighter operations had never achieved. The concentrated firepower of Lightning formations, combined with coordinated attacks that prevented German pilots from using their superior maneuverability, demonstrated the effectiveness of American technological advantages when properly employed. The psychological impact of these encounters extended far beyond immediate tactical results. German pilots who had dominated every opponent they faced suddenly found themselves confronting an enemy that possessed decisive technological advantages. The P-38's ability to engage when conditions favored American pilots while disengaging when they didn't created a form of psychological warfare that gradually eroded German confidence and initiative. Hauptmann Hans Arnold Stahlschmidt, commanding officer of 3/JK-53, reported that his experienced pilots were becoming increasingly reluctant to engage P-38 formations unless they possessed overwhelming numerical superiority. This reluctance reflected a fundamental shift in air combat dynamics. German pilots, who had always dictated the terms of engagement, found themselves reacting to American initiative rather than maintaining tactical control.
British. What neither side fully understood was that the Lightning represented more than just another fighter aircraft with better performance specifications. It embodied a completely different philosophy of air combat, one that emphasized technological superiority, operational flexibility, and strategic capability over traditional tactical considerations like maneuverability and pilot skill. The confrontation between these competing philosophies would reshape aerial warfare and challenge fundamental assumptions about fighter design that had dominated military thinking since the dawn of aviation. The war was about to discover whether German confidence in conventional fighter doctrine and pilot training could withstand the challenge posed by American technological innovation and industrial capability. In the process, both sides would learn that the future of air combat belonged not to those who had perfected existing techniques, but to those bold enough to imagine entirely new approaches to the ancient art of aerial warfare. August 14, 1942. 13:47 hours. The Focke-Wulf Fw-200 Condor that had seemed so secure moments earlier was now a falling torch, its starboard engine streaming fire as it spiraled toward the frigid North Atlantic. The P-38 Lightning that had delivered the killing blow pulled up sharply, its twin engines singing their distinctive note as pilot Second Lieutenant Elza Schahn banked away from his first kill. In those few seconds of combat, the aerial warfare had changed forever. though neither side yet understood the full implications of what had just occurred. The German crew's final radio transmission, intercepted by Allied listening posts, contained a phrase that would be repeated countless times in the months to come. Descriptions of an American fighter that seemed to appear from nowhere, strike with devastating firepower, and disappear before German escorts could respond. The lightning's speed advantage, combined with its concentrated armament, had demonstrated a new form of air combat that traditional fighter tactics couldn't effectively counter. The shock of first contact. Within hours of Schon's victory over Iceland, reports began filtering through Luftwaffe intelligence networks about encounters with an unusual American twin-engine fighter. Initial reports were dismissed as pilot error or misidentification. Experienced German aviators simply couldn't believe that a twin-engine aircraft could outperform their proven single-engine fighters in air-to-air combat. The skepticism was understandable given German experience with their own twin-engine fighters. The Messerschmitt Bf-110, despite its heavy armament and long range, had proven vulnerable to agile single-engine opponents during the Battle of Britain. Luftwaffe doctrine had relegated twin-engine aircraft to ground attack and reconnaissance roles, considering them unsuitable for air superiority missions against competent opposition. But the P-38 encounters reported by surviving German pilots described performance characteristics that seemed impossible for a twin-engine design. Luftwaffe pilot reports documented an aircraft that could outrun their fastest fighters in level flight, outclimb them at high altitude, and deliver concentrated firepower that could destroy aircraft with single bursts. These capabilities violated everything German fighter doctrine assumed about twin-engine aircraft limitations. Oberst Adolf Galland, one of Germany's most experienced fighter commanders, initially refused to believe intelligence reports about P-38 performance. His extensive combat experience against British twin-engine fighters was convinced that German single-engine fighters maintained decisive advantages in speed and maneuverability. His skepticism reflected broader German attitudes that would prove increasingly dangerous as P-38 encounters became more frequent. The first documented encounter between German fighters and P-38s in the European theater occurred over North Africa in November 1942. A formation of Messerschmitt Bf-109s from Jagdgeschwaden 53 intercepted what they expected to be easy targets, American twin-engine fighters that intelligence had warned them about, but that no one took seriously. The result was a tactical disaster that shattered German assumptions about American aircraft capabilities. The 82nd Fighter Group's arrival in North Africa marked the beginning of systematic P-38 operations against experienced German pilots. On November 28, 1942, Bf-109 pilots claimed 7 Lightnings for no losses of their own, seeming to confirm German expectations about twin-engine fighter vulnerability. But this initial success masked a troubling reality. The P-38 pilots were still learning to exploit their aircraft's advantages, while German pilots were encountering capabilities they didn't understand. Captain Bill Sloan of the 82nd Fighter Group exemplified the learning process American pilots underwent. During his first encounters with German fighters, Sloan attempted to engage in traditional turning fights, negating the P-38's speed and firepower advantages. German pilots, fighting according to proven tactics, achieved easy victories against Americans who were essentially fighting with one hand behind their backs. But Sloan and his fellow P-38 pilots were quick learners. Within weeks, they had developed new tactics that exploited the P-38's unique capabilities while avoiding prolonged dogfights where German experience and training provided decisive advantages. These new tactics would gradually shift the balance of air combat in ways that German pilots found increasingly difficult to counter.
British. The most significant P-38 mission of the war occurred on April 18, 1943, when 16 Lightnings intercepted and killed Admiral Isoroku Yamamoto, architect of the Pearl Harbor attack. The mission demonstrated capabilities that no other Allied aircraft could have accomplished, flying nearly 1,000 miles over enemy territory to intercept a specific target at a predetermined location and time. The Yamamoto mission required navigation precision, fuel management, and operational coordination that pushed P-38 capabilities to their absolute limits. Major John Mitchell's planning had to account for wind patterns, fuel consumption rates, and timing requirements that allowed no margin for error. The success of the mission validated American confidence in the Lightning's long-range capabilities, while delivering a psychological blow to Japanese morale that exceeded its immediate tactical significance. Captain Thomas Lanphier and Lieutenant Rex Barber, the pilots credited with shooting down Yamamoto's transport, exemplified the combination of technical competence and tactical innovation that characterized successful P-38 operations. Their ability to manage complex fuel systems, maintain precise navigation over hundreds of miles of ocean, and deliver accurate firepower when the critical moment arrived demonstrated the effectiveness of American training programs and aircraft systems. The German response to increasing P-38 effectiveness reflected their recognition that traditional fighter tactics were inadequate against an opponent with decisive technological advantages. Luftwaffe training programs began emphasizing hit-and-run tactics similar to those employed by American pilots. But German aircraft lacked the speed and climb rate advantages necessary to execute these tactics effectively. The European challenge. P-38 operations in the European theater presented different challenges from those encountered in the Mediterranean and Pacific. The weather conditions, high-altitude requirements of bomber escort missions, and sophisticated German air defense systems created operational environments that pushed P-38 capabilities in new directions. The 55th Fighter Group's arrival in England marked the beginning of systematic P-38 operations over Western Europe. Their first mission on October 15, 1943, coincided with the disastrous Schweinfurt raid, where German fighters destroyed 60 of 291 B-17 bombers, in a demonstration of what unescorted bombing operations could expect against determined opposition. P-38 pilots found that European operations required different tactics than those developed in other theaters. The concentrated German fighter opposition and sophisticated early warning systems meant that P-38 formations often faced overwhelming numerical odds against experienced pilots flying aircraft specifically designed to counter American bombing operations. Lieutenant Colonel Jack Jenkins, commanding the 55th Fighter Group, developed new tactical formations that maximized the P-38's firepower while providing mutual protection against German fighters. These formations emphasized coordination and discipline rather than individual initiative, reflecting the more structured nature of European air operations compared to the fluid situations common in the Pacific theater. The psychological impact of P-38 operations extended beyond immediate combat results. German pilots who had maintained air superiority over their own territory found themselves facing an opponent that could escort bombers to targets throughout Germany, while maintaining the capability to engage German interceptors on favorable terms. Technological evolution. By 1944, both sides had learned from 2 years of P-38 combat operations, leading to tactical and technological adaptations that reflected the aircraft's impact on aerial warfare. German aircraft designers attempted to develop fighters with performance characteristics that could match the Lightning's advantages, while American engineers refined the P-38 systems to address limitations revealed through combat experience. The P-38J model incorporated improvements that addressed most of the aircraft's early problems. Power-assisted ailerons improved roll rate. Dive recovery flaps eliminated the compressibility problems that had killed early test pilots, and improved cockpit heating systems made European operations more practical. These modifications transformed the Lightning from a promising but problematic aircraft into a mature weapons system that could compete effectively against any opponent. German countermeasures included new tactics, improved aircraft, and technological innovations designed to neutralize American advantages. But the fundamental problem remained. German single-engine fighters, regardless of their performance improvements, could not match the P-38's combination of speed, range, and firepower that allowed American pilots to choose when and where to fight. the strategic bombing campaign's success depended largely on the P-38's ability to escort bombers to targets that had previously been beyond fighter range. German air defenses, designed to counter unescorted bombing operations, proved inadequate against coordinated attacks by bomber formations protected by fighters that could maintain formation throughout extended missions. The final verdict.
By war's end, P-38 Lightning pilots had achieved a combat record that validated Kelly Johnson's revolutionary design concepts while demonstrating the effectiveness of American technological innovation when properly applied. In the Pacific Theater alone, Lightning pilots destroyed more Japanese aircraft than any other American fighter, while the top two American aces of the war, Richard Bong with 40 victories and Thomas Maguire with 38, both flew P-38s. The aircraft's impact extended far beyond individual combat statistics. The P-38's long-range capabilities, concentrated firepower, and high-altitude performance had fundamentally altered the strategic balance of air warfare. Allied bombing operations that would have been impossible with conventional fighters became routine with P-38 escorts, while reconnaissance missions provided intelligence that shaped strategic planning throughout the war.